Welcome back. In the last session, we started integrator and we had seen passive integrator and we had seen the conditions for the passive integration. Now we are seeing active integrator. Therefore, if you consider active integrator, last session we started the derivation to get the relation between V0 to Vi. Then we were applying nodal analysis and we took virtual current concept because capacitor is acting as a feedback component. Therefore, negative feedback, virtual current concept is valid. This is 0, this is 0. Current leaving from this node 0 minus Vi divided by R plus current leaving from this node is nothing but current flowing through the capacitor. C into dV by dt is equal to 0. But the voltage across the capacitor, if you take this is what is the current direction, right? Then this is another plus minus Vc. But what is plus minus Vc? Voltage at this point minus voltage at this point. Voltage at this point is 0 and voltage at this point is V0. Therefore 0 minus V0, that is nothing but your Vc. This is what we discussed in the last session. Now let us substitute that Vc in equation 1. Then what you get? Therefore 1 implies, tell me, C into what is dVc by dt? Vc is nothing but minus V0. Therefore minus dV0 by dt is equal to Vi divided by R. Then tell me what is dV0 by dt? Therefore dV0 by dt is equal to minus 1 by RC into Vi. Then can you do integration on both sides? Then you will get V0 of t or V0 is equal to minus 1 by RC, that you can take it as constant, integration of Vi into dt. Therefore what is V0 to Vi relationship? V0 is equal to integration of Vi into dt. That 1 by RC is nothing but the gain term, right? Why are we getting negative sign? Because applying input at inverting terminal. Because input is applied at inverting terminal, your output to input relation will be opposite. Okay? And 180 degrees for sinusoidal signals. Therefore, let us say R is equal to 1 kilo ohm and C is equal to 1 microfarad. What does it mean? 1 kilo into 1 microfarad. Therefore 1k into 1 micro, 1 milli, 1 by 1 milli, it will be kilo. Therefore indirectly that is the gain term. Okay. Therefore 1000 times of integration of your input signal is nothing but your output. If you take R is equal to 1k and then C is equal to 1 microfarad. I'm just taking one example. Therefore it is not only doing integration, it is also doing amplification, provided the triangular wave output peak to peak should be less than the power supply peak to peak of your op-amp. We cannot go more than VCC of your op-amp. We cannot go below minus VCC of your op-amp. That should be in between plus VCC to minus VCC. Then whatever gain term or whatever proportional constant you have along with the integration of your input signal, right? With that if you calculate V0, then it should be within plus or minus VCC. Else you see clipping. It is trying to cross but it cannot cross, then you see clipping. That is what is called signal is distorted. That we need to consider practically. Okay? That is fine. Take it. This is what is our active integrator. Okay. Assuming op-amp is ideal. Assuming op-amp is ideal. Only op-amp is ideal means gain is very high. If gain is very high, then only virtual current concept is valid, even though it is in negative feedback. Because I told that if op-amp is in negative feedback, we can use virtual current concept. Not only that, your gain of op-amp should be very high. Then only you can use virtual current concept, even though it is in negative feedback. It is simple, right? Some simple nodal analysis. We got the equation V0 to Vi. Similarly, we need to do for differentiator. First of all, passive differentiator, then active differentiator, right? Okay. I'll give you 30 seconds. Try to complete it. I think this is already covered in the last session. Now this is what is our incremental part. Done? Now write down differentiator. Whatever we have seen in the case of integrator, let's try. Okay, now differentiator. Okay, what is differentiator? Again, same thing. The circuit which differentiate your input signal. That is what is a differentiator, right? What is the symbol? D by dt. Time domain, right? Therefore, let us say this is V naught of t and V of t. Again, what I am trying to do is, we are just considering a system with black box, assuming that it is doing differentiation. Then V naught of t is equal to differentiation of your Va of t. To get differentiation between input to output, right? Then what is the condition? That is what I am trying to derive from generic or requirement. Then the circuit which satisfies that requirement, maybe in time domain or frequency domain, that is what is your differentiator. Okay, let's see. Now what is V naught of t is equal to d by dt of Va of t, right? Then apply. Then what is this? This is nothing but Va of s. Then what is V naught of t? V naught of t is equal to V naught of s is equal to what? Tell me. If Va of t is Va of s, then differentiation of Va of t in s domain into s into Va of s. In the case of integration, 1 by s, but in the case of differentiation, that is s into Va of s. Then what is transfer function? H of s is equal to V naught of s divided by Va of s. What is that? That is simply s, right? This is H of s. Then what is H of j omega? Then H of j omega is equal to j into omega. Then if I take magnitude, mod H of j omega is equal to omega. If I convert into dB, what you will get? Mod H of j omega in dB is equal to 20 log omega. Then if you plot the frequency response, either you can take omega or f, anything is fine. Okay, when I say this is what is 1, this is what is 0 dB, this is what is your mod H of j omega in dB. Therefore now tell me, as omega is increasing, omega is 10, 20 dB, 100, 40 dB, 1000, 60 dB. Therefore, if you see, this is what it is. Let us say this is 10, this is 100, this is 1000, enough, radians per second. This is nothing but radians per second. Okay, now tell me, what is the gain? This is 20 dB. Then what is this gain here? This is 40 dB. Then what is this gain? 60 dB. Therefore, the system which has the gain, plus 20 dB per decade, that is what is having differentiation. This is what is having the slope plus 20 dB per decade. If it is minus 20 dB per decade, integration. If it is positive slope plus 20 dB per decade, if gain increases linearly, right, with the slope 20 dB per decade, then that is what is having differentiation. Tell me, do you have any system which has the slope plus 20 dB per decade? High pass filter, your high pass filter, or band pass filter, low frequency range, right? Therefore, let us consider high pass filter. What is high pass filter? Just swapping off resistor and capacitor. Now this is your V naught of t. Now this is V of t. Okay. Now, but we want to write in frequency domain. I am trying to explain the things in frequency domain. Therefore, let me say this is what is Va of s. Then this is V naught of s. Right. Then tell me what is transfer function. Now H of s is equal to, tell me, R divided by R plus 1 by SC. right? Then SC it will go to, therefore it will become SCR divided by 1 plus SCR, right? Then, or I can say, maybe to make it easier, what I do, can I take R as LCM? Sorry, common. Then RR will be cancelled. 1 plus 1 by SCR. This is what you'll get. Can I say that? Yes. Then what is H of j omega? H of j omega is equal to 1 by 1 plus j into omega into RS. Right? Then what is this? Therefore, H of j omega is equal to 1 by 1 plus j into 2 pi f into r into c. Right? Can I write this as like this? Therefore, H of j omega is equal to 1 divided by 1 plus if you see here, how can I write? Sorry, something is wrong. Is it 1 plus j omega RC? 1 by j omega RC. 1 by j omega RC. Therefore, 1 by, it will become minus j, okay, because plus j into minus j, then it will become j into j, minus j 1 by 2 pi RC divided by F. Can I write like this? Yes, it will be j by 2 pi f into RC, but I have taken 1 by 2 pi RC as one constant and then 1 by f. Both are same. Therefore, now tell me 1 by 1 minus, it is nothing but what? J into FL divided by F, where FL is nothing but where FL is equal to 1 by 2 pi RC. This is what is lower cutoff frequency. Therefore, tell me what is mod H of j omega? Mod H of j omega is equal to 1 by 1 plus FL divided by F whole square. This is what is our magnitude, right? Now, if you plot the frequency response, right, using this is what is real equation or accurate plot. But if you use Bode plot, we have what? Actually, if you use Bode plot, we'll have 1 0 and 1 pole. Okay. Therefore, according to Bode plot, when I say this is what your frequency, according to Bode plot, mod H of j omega, let us say in dB, if you convert into dB 20 log of this. Okay. Now, there is a what? There is a pole at FL and there is a 0 at 0 frequency. If there is a 0 at 0 frequency, then according to Bode plot, the frequency response will have plus 20 dB per decade. Then let us say there is a pole here which is nothing but FL. What is FL? 1 by 2 pi RC. Wherever there is a pole, the frequency response will have a slope minus 20 dB per decade. Because of pole, minus 20 dB per decade, but because of 0, plus 20 dB per decade. Plus 20 dB per decade, minus 20 dB per decade, both will be cancelled. You'll get flat response because of 0, pole 0 cancellation. Therefore, according to Bode plot, this is what is our frequency response. Because if you take H of S, what is this? This is nothing but SCR divided by 1 plus SCR. SCR is equal to 0, S is equal to 0. There is a 0 at 0, right? And 1 by 1 plus SCR, SCR by 1 plus SCR. Therefore, there is a pole at 1 by RC minus 1 by RC. Therefore, which is nothing but 1 by 2 pi RC. Therefore, because of 0 plus 20 dB per decade, but because of pole minus 20 dB per decade, both will be cancelled. You will get 0 dB per decade. But this is what is according to Bode plot. But if you take actual curve is nothing but what? As Fe is increasing, your gain will increase, right? Then your gain will increase. If you observe clearly, then this is what it is. Actually this is what is real plot. Okay, slowly the cancellation is happening. Okay, then it is reaching to 0 dB per decade. Okay, whatever maybe. Therefore now this is what is your 3 dB point. Okay, this is what is a 3 dB point, and this is what is your maximum gain you can get. Okay, when gain is equal to 1, when when the value of F is very much greater than FL, then it is almost 1, then this is nothing but 0 dB, right? This is what is your 0 dB. Now this is what is minus 3 dB. Therefore this is the reference. What at maybe this is what your lower cutoff frequency. Okay, leave it. What at maybe where do you have slope of 20 dB per decade? That is what is our high pass filter. Actual frequency response is the red one, but according to Bode plot 20 dB per decade and then 0 dB per decade. Okay, therefore this is what is the portion you have 0 dB per decade, and this is the portion you have plus 20 dB per decade, plus 20 dB per decade. Therefore you can use this frequency range as your what? Differentiator. High pass filter or whatever, this is what is your differentiator. Therefore tell me, your high pass filter is acting as differentiator. It is acting as a differentiator only if the frequency of your input signal should be very much less than FL. If the frequency of the input signal is very much less than 1 by 2 pi RC, then only you are getting the slope plus 20 dB per decade, then you can use it as a differentiator. Not just less than FL, because if you take actual curve, actual frequency magnitude response, that is not having plus 20 dB per decade, slowly that plus 20 dB per decade is becoming 0 dB per decade. Right? That's why very much less than, far less than FL. Here almost you can say black or red, I can say having plus 20 dB per decade, there you can use the high pass filter as a differentiator. Okay, take it, then I'll explain using time domain. Then after that we will see active differentiator. Okay, take it. The final condition to remember is your RC circuit is acting as a high pass filter, and that high pass filter can be used as a differentiator only if the frequency of your input signals is less than, very much less than 1 by 2 pi RC, or slow of cutoff frequency. Okay, now time domain analysis. Now time domain analysis. Okay. Now if you consider this is V naught of t, V of t. Let us give square wave as input. And this is 0 to t. This is 0. This is t by 2. This is t. This is plus V minus V. This is V of t. Okay. Let us say this is what is the input. Now let's see what is the output for this. Okay. Now again let's consider 3 cases. This is what is time t. Now what is the input? Let me explain qualitatively. That is enough to get the condition of differentiation. Okay. This is what is continued. Okay. Now we want to get V naught of t. Now let me take case 1. Case 1 is nothing but your RC is very much greater than t by 2. What does it mean? See, whether you are taking your output voltage across the resistor or you are taking output voltage across the capacitor, doesn't matter. Ultimately it is in the loop. The loop is having the time constant of R into C. Okay. Whatever may be, we are trying to, whatever input you are applying, your capacitor is trying to charge to that voltage. But we are not taking voltage across the capacitor. Now we are taking voltage across the resistor. But it has to satisfy KVL. What is KVL? Your input voltage VI is equal to the voltage across the capacitor plus the voltage across the resistor. Right? Now, if I say that, tell me when RC is very much greater than T by 2, means the time constant of the circuit is very much greater than T by 2. In the time of T by 2, your circuit RC or the capacitor cannot charge because the time constant is very high. If time constant is very high, then tell me what can be the output? Because we are not taking voltage across the capacitor, we are taking voltage across the resistor. Now input is changing suddenly. When input is changing suddenly from 0 to V, voltage across the capacitor cannot be changed instantaneously. Then this voltage is equal to this voltage plus this voltage. Let us say the voltage across the capacitor is 0. Then whatever step you have 0 to V, that step will come to the resistor because voltage across the capacitor cannot change instantaneously. Whatever sudden change you have at the input, that you see at the voltage across the resistor. Therefore, we will see this. Now, but now the capacitor is charging very slowly because the time constant of the circuit. The time constant of the circuit is very much greater than T by 2. In this time, your capacitor cannot charge. If capacitor is not charging, it is almost at 0, then what does it mean? Your output voltage will be almost at V, whatever you have, because this voltage is equal to this voltage plus this voltage. If this is almost 0, then whatever you have, which is nothing but V, that V will be here. But we know that it will charge very slowly. When this is charging very slowly, the voltage across the capacitor is increasing very slowly. Then the voltage across the resistor will decrease slowly because this voltage is equal to this voltage plus this voltage. Your input is V. Out of V, some voltage is going across the capacitor. Remaining voltage will be coming across the resistor. Then slowly, because capacitor voltage is increasing exponentially, the voltage across the resistor decreases exponentially, and that is what is decreasing exponentially. But now your capacitor is charging, but it is taking huge time to charge. Then the resistor is discharging. When capacitor charges to V, then the voltage across the resistor will become 0 because V is equal to the voltage across the capacitor plus resistor. If the voltage across the capacitor is charging and then reaching to V, then the voltage across the resistor will be going to 0. But you know, your input got changed suddenly from plus V to minus V. Then input is changing from plus V to minus V. But voltage across the capacitor cannot change instantaneously. Whatever change you have from plus V to minus V, which is 2V, that delta you have to see across the resistor to satisfy KVL. Whatever change you have seen at the input, there is no change in the capacitor because voltage across the capacitor cannot change instantaneously. Then whatever change you have at the input, the same amount of change you can see across the resistor. But here input is decreasing from plus V to minus V, your output also will decrease from plus V to whatever it has from there to V. It has something here, then from here it will have 2V delta. This is what is 2V step. Now your capacitor is trying to charge to minus V. When capacitor is trying to charge to minus V, then if it is charging completely to minus V, then your voltage across the resistor is becoming 0. Ultimately, the voltage across the resistor is trying to becoming 0 because voltage across the capacitor is trying to become minus V. If the voltage across the capacitor is becoming minus V, then the voltage across the resistor will become 0. But it is discharging very slowly because RC is very much greater than T by 2. Then it is what is going very slowly. But suddenly your input is changing from minus V to plus V. When input is changing from minus V to plus V, voltage across the capacitor cannot change instantaneously. Whatever step you have at the input, the same step you are getting at the output. Okay? Therefore, this is the step. And this is what we are going to get it continuously. Tell me, what is differentiation of square wave? Differentiation of square wave is nothing but impulse. Is it impulse? Means positive impulse, negative impulse, positive impulse, negative impulse. Is it impulse? No. Right? Case 2. If RC is equal to T by T, same thing. Right? Then what we get? Let me use different color. Now the color is, let us say, blue. RC is equal to T by T. Therefore, it charges a little bit faster than case 1. When it charges a little bit faster than case 1, then what you get? You will get it like this. Okay? Okay? Why it is decreasing little bit fast? Your capacitor is charging quickly because RC is equal to T by 2. Your capacitor is charging quickly, then the voltage across the resistor is becoming 0, little bit faster. Then you are getting. But how much is the change at the input, which is plus V to minus V? The same amount of change you have to see at the output of resistor because voltage across the capacitor cannot change instantaneously. Whatever you have, 2V change you have to see. Then again it is trying to charge to 0 because capacitor is charging to, trying to charge to minus V. KVL, it is simply KVL. And the point is voltage across the capacitor cannot change instantaneously. Now the last case, case 3, RC is very much less than T by 2. What does it mean? Your capacitor charges very quickly. Within a given time of T by 2, your capacitor charges to the voltage what you apply. Then tell me, but voltage across the capacitor cannot change instantaneously. Initially have the step, but in a time of 0 to T by 2, your capacitor charges to V. If capacitor charging to V, this voltage V is equal to V plus 0. Therefore, voltage across the resistor will become 0. Then immediately it will become 0 because capacitor is charging very quickly. Then this is what is capacitor charged and this is what is 0. But input is changing from plus V to minus V. Voltage across the capacitor cannot change instantaneously. Whatever input you have, which is plus V to minus V, that you have to see across the resistor. Then it has to have 2V change. Okay? Then immediately your capacitor will charge to minus V, but the voltage across the resistor immediately it will become 0. Again, you will see this. It will discharge. This is what it is. Kind of triggers or kind of impulses you are getting at the output. But remember, the impulse function step, that is 2V. This is 2V, this is 2V. Not more than that. Therefore, total peak to peak, if you ask me, that is 4V. Whatever 2V you have, that 2V is becoming 4V. But ideally, we are expecting it to be, amplitude to be very high. then that is what is called impulse. But practically it is not impulse, but it is having huge strength. Therefore, just listen. Therefore, this is what is case 1. This is nothing but case 1 where RC is very much greater than T by 2. Now the red one is nothing but case 3 where your RC is very much less than T by 2. Therefore, we want this condition to get to say that it is doing differentiation. Therefore, tell me your RC circuit or high pass filter. Your high pass filter is acting as a differentiator. It is acting as a differentiator only if condition RC should be very much less than T by 2. For 2 into RC should be very much less than T, then 2 into pi, let us say this is T, then 1 by 2 pi RC is very much less than 1 by T. What is this value? The lower cutoff frequency FL is very much greater than F. Therefore, the frequency of your input signal should be very much greater than FL. Is it true? Because when you do reciprocal, it will become very much greater. Okay. Therefore, this is what is very much greater. Now, your F should be very much less than FL. This is what we got from what? Frequency domain analysis. The same thing is expected from time domain, but we are understanding what's happening inside the circuit. That is what is our time domain analysis. Okay. Take it. After that, I'll explain what is active differentiator. Okay. Continue. Done? Let me wait for 30 seconds. Then I'll give you active differentiator. With that I can say differentiator is also over. See, these circuits will use when I explain about some multi-vibrators. Okay? Because these will be used as a trigger pulses. Done? Okay. Just swap the components from your integrator. You will get the differentiator. Right? Now, negative feedback or positive feedback? Negative feedback. Virtual ground concept is valid? Yes. Then, this is what is 0. Now, let us say this is what is plus minus voltage across the capacitor VC, and this is what is current through the capacitor IC. Okay? Now, tell me, according to nodal analysis, current leaving from this node is nothing but IC. What is that? C into dVc by dt plus current leaving from this node is equal to 0 minus V0 divided by R is equal to 0. Right? Therefore, what is V0? Therefore, V0 by R is equal to C into dVc by dt. Therefore, V0 is equal to RC dV0 by, dVc by dt. We call this as equation 1. What is Vc if you take the capacitor? Right? This is what is plus minus Vc, but this is 0 and this is Vi. Right? Then what is Vc? Vc is equal to 0 minus Vi, which is minus Vi. Therefore, tell me, one implies your V0 is equal to what? Rc into minus. Therefore, minus Rc into dVi by dt. Therefore, what is your output? Your output is equal to what? It is not only doing differentiation, right? Practical differentiation is nothing but if you apply square wave, it is trying to give you impulses. Then RC is the one which is what limiting the impulse, and then maximum and minimum it can go is nothing but plus or minus VCC. Not more than VCC, not below VCC, minus VCC, you can get at the output of your Opamp because it is limited with respect to power supply. Okay? Minus is indicating what? Inversion between input output, because Vi is at inverting terminal of your Opamp, that's why V0 is inversion of your input. But this is what is some constant into dVi by dt, differentiation of your input. That is what is our active differentiator. If you compare with passive differentiator, it is having some gain. It is having some gain. But it deals with spikes. That's why people don't use differentiator. If you can solve anything using integrator, people go ahead with integrator. Don't use differentiator because it deals with spikes, triggers and all. Then circuit is little bit, it will be damaged. There is something called reliability validation, then it will be damaged. Due to which people don't use differentiator, provided if you have the solution with integrator. Okay, take it. We have 3 more minutes for the session. Try to complete within 3 minutes, then which is more than enough. 2 minutes, more than enough. Then we will see the next part. Okay, that we will continue in the next session. You can take in the meantime. Next session we will solve few problems, classroom problems. Okay. If you observe clearly, if you apply virtual ground concept, this is at 0, virtually 0, taking output voltage at this node, which is nothing but taking output voltage at the resistor with respect to ground, means taking output voltage at the resistor. That is what is the RC circuit also. We are taking output voltage at the resistor in the case of differentiator. That is what we are doing in the case of Opamp also. Okay. We will continue in the next session. Thank you.